Fine. So the next question is from the medium bucket, and this question is from the tree data structure. And we are given with a complete binary tree, and we have to do is count the number of nodes. So I guess everyone knows about a complete binary tree. So here is a beautiful definition of binary tree, a complete binary tree. So in a complete binary tree, every level has like a maximum number of nodes it can have, and but the last node, the last level uh, can have like minimum number of nodes, and the the tree can be as far left as possible. So this is the simple definition of complete binary tree. So we have to count the number of nodes. So over here we have 6 nodes, and so output 6. Is there any question regarding the problem statement? Fine. So anyone who would like to tell his or her approach?
So what I tried, like without like a brute force, I would say, I just I saw this as a counting the number of nodes present. So I did it by doing a level order, like how many nodes are there in each level, and that would be our answer.
Well,
Okay, so how are you getting? Yeah.
The brute force is just traverse whatever, right? In order, post order and count number of node, right?
So, but I did by level, so something like that.
So how did you went like level by level? Like what was your approach? Like
So just put first node in a queue, and then it's then count like while popping while dequeuing it, you count how many are coming, and if that node has left and right child, then you just need to add that in a queue.
So you did this in an iterative way or a recursive way?
Yeah, it's an iterative way.
Okay, fine.
The thing with that is you need extra space for the queue.
Yes, and its time complexity is also increasing because I am visiting each node.
I think the time complexity will be the same because you touch each node only once.
Right. Time complexity will be same.
But if you know that that complete binary tree, like we know the complete binary tree is like its left hand child, right child would be there. You just need to check the last level. Then I think that time complexity can be reduced by checking just the last level.
Yeah, we can use the property of complete binary tree, like Sonia said. Like every level has 2 to the power I number of nodes at max, and we just have to check for the last level, as the only the thing that can vary is just the last level. So
yeah.
And one of the things that we note in this incomplete binary tree is if we can go in the reverse order instead of going from the left and right. First, let's check for the right, because the missing nodes will be closer to the right end. Like if we go from 1, then 2, then 4 and 5, it will be traversal of entire tree just to find that one node which is missing, 7th one. So if we go in the reverse way, like looking at the right node first, we'll find the first one which is missing, maybe like 7th, and then just we have to check is whether 3 has other node or not. And if that is not there, then we can go to the 2. And if we find 6, we are definitely sure the rest of the nodes are there. So instead of counting them, we can use a rule of elimination to find out which ones are missing.
So you keep track of the depth of the tree when you go to the right?
Yeah, we'll go to the right and find out the first one which is missing a right child. Right? And then we can go back and then check if it's having a left child and all, and then we can check if that's the last level. So if it's complete binary,
suppose that for in the example, let's suppose 5 and 6 does not exist. So
Right.
how would your algorithm go?
So yeah, if you're saying it's 5 and 6 is not existing, then it will go from right. So it will be essentially like DFS, but in the reverse order. Like instead of left, right child, will go by right, center, and left. If 5 and 6 are not there, it will be essentially similar to a complete DFS. I'm just saying, the more chances are there, or the more probability is of having right side nodes missing.
So if you're saying that it's doing a BFS, then also we are visiting each and every node.
So in worst case scenario, yes, you will be visiting all the nodes when you are having, or when this is completely a complete binary tree. So you'll always be visiting every node to check it out if it's already a fixed complete binary. I'm just saying, if you want to find out the most probabilistic one where the things will be removed, that will be the rightmost end, because if it's not complete, then the order of removal of nodes will be from the rightmost end to the leftmost.
Yeah.
Because the seventh one, if I have to remove, it will be on the right hand side.
Yes.
That's just kind of not an asymptotic optimization, but just a logical optimization.
Mm-hmm.
I just did in a recursive way. Like if the root is not equal to null, then I just added 1 to the count nodes, and then I did root dot right plus root dot left. So it's just a recursive call I did, and I got a AC out of it. So when
I don't know why it is called complete count of trees, because it is just simply counting the number of
yeah,
nodes.
because I haven't used the property of a complete binary over here.
Exactly.
I just did a normal count of nodes.
No, actually,
No, does it
so
clear?
in the
I don't
same
think it will
input,
clear.
sorry, so in the same input, if you give like in between 5 and 6, can you also put a null, like 1, 2, 3, 4, 5, and then null and 6? You have to get 5 nodes, because that is the proper example of a complete binary tree. So right
Problem
now
is
the
the
tree
question
left
itself.
is 5.
The question itself says it's a complete binary tree, so we'll not have that null scenario. The first statement is it's a complete binary tree.
Oh, given a complete binary tree, count the number of nodes, please. Yeah,
Yeah.
I understand what you're saying, that you will put you'll put a null on the left side of 3 and then 6.
The
That
input
is not a
itself is
complete
wrong.
binary tree.
Right.
In that case, then the sense makes to check whether right and left everything is. So we'll have to check every sub node is also a complete node. That in itself has to be a complete node.
My thinking is like if we look at the input, and if we see that if we extract only 1, 2, and 3, that's a full binary tree, right? So if we go, we can extract it out, and we know, okay, we know we can count like how many nodes on that subtree. Then we go down, we recursively treat 2 as a root, and count how many node start at root at 2, and similarly do for 3.
Yeah, exactly. That's what we were saying, that at every sub node, when you from 1 to 2, you'll again have to check that subtree is also a complete tree.
Yeah.
So like in this case of 2, 2, 4, 5 is a subtree, and then we can move one step up. If any of the subtrees is given a result as no, it's not a complete tree underneath, then the complete tree cannot be the entire tree cannot be a complete tree.
So we break the problem down to multiple sub problem, right?
Right. It's a recursive same problem, but just with a different root now.
So this solution will work for even if it is not complete binary tree, right?
Right. That's the idea.
So I'm thinking about one other approach. I did it with that. We know that by using the complete binary tree problem that if one of the thing is like we know that uh, our left side would be a complete binary tree because the nodes will complete left first, correct? At left side, as it's written that the last level, the nodes will be at the left side first,
Right.
then it would be a right side.
Right.
So if while like if we find the depth, like simply finding the depth of the node and and checking that if the left, like taking the left and the right height of the like depth of the left and right side, and if they are equal, then we mean it, which means that our left part is a complete binary tree. Like left subtree is a complete binary tree, which is like 2 raised to power how much depth we have in the left side, and then we can recursively count the right side of the tree. Otherwise we'll do a reverse, like if they are not same, then we can do a reverse by forming the by which then we mean that means that we have a complete tree on the right side and we need to count the nodes on the left side.
Can you give us a drive in for this? Like, I'm not getting.
Yeah.
Shall I show you my screen?
Okay, okay. Let me stop my.
Yes, 1 second. I'll just open the question.
Yeah.
1 second. Can you see my screen?
Yeah.
Yeah.
Yeah, so this is one solution. Like this is the function for finding the depth, which is like normal finding the depth for one of the node. And instead of just starting from the root, I have started from the left and right, like 2 subparts. And here I'm traversing for the left part, and here I got the right part. And if the left and right is equal, then I'm just taking the, like I know that the left subtree will be a complete binary tree, and just taking the power of it, and then again recursively calling the right side of it. Otherwise it will be reverse. It's just
this you still need to get the depth of a given node, right? So potentially you could have touched other node in the tree.
yeah.
So this, this still like same as the brute force.
But here I'm not touching all the nodes because taking a depth, and I know there would be a if they match, that would be a
You don't
that
know
would be 2 raised to
it
power
match
how
or
many.
not until you count you touch every node, right? First you have to you go depth first.
Yeah, I am going to the depth first. Correct.
One more
But
thing
she is
is
only looking at left if you look at it.
Yeah.
She's not looking at the right node. So she will always get the height. And since this is a complete binary tree, she is looking at the height of that complete binary tree, which is log n. So that is just log n calculation. And at every step, since she is distributing the tree into 2 halves, like with recursive call, this will become log n into log n, which is log square n, you can call. That's the complexity she is achieving with this approach.
Sonia, this will work if, given the condition in a tree that it's already given a complete binary tree.
Yeah, because
coming to the discussion which we had, like if we had to check both the things, like whether the tree is a complete binary tree and then count the number of nodes, then probably this one will not work. If you have a skewed tree, like 2 nodes down the left, it's 2, and then you have everything skewed towards the right. So then in that
Yeah,
case,
that would be not that actually that then it's not a definition of a complete binary tree.
right. I'm just saying, just this approach works fine for the problem statement.
Yeah.
I'm just, trying a different version. If there is like, it's not given a complete binary, it's just given a tree, and then we have to count whether it's a complete tree and the number of nodes.
Yeah. Okay.
Or maybe a different variation that I can think of is count the number of nodes or count the number of nodes in the entire tree which form a complete binary, complete tree. Like maybe in this case, if there was no 6 in that, it would entirely be also a complete binary tree. But now if we consider there's no right node towards 1, you still have one binary tree or one tree which is complete, which is 2, 4, and 5. Just a variation of this kind of problem.
Like if we don't have any 6 in that side?
6 and 3, both of them are not there. And the question says that you have to count the number of nodes which do form a complete tree.
Then it's simply the depth formula which is finding the depth of the tree.
No, that will not be there because anything which is rooted at 1 will not be a complete binary tree. But what is rooted at 2 will become a complete binary tree. I hope I'm clear. If not, I can share my screen and probably.
Yeah, you can share your screen and please help.
Sure. Is the screen visible?
Not yet. It's blank. Yeah. Now it's.
Yeah. Okay. I was just saying, if there's a tree like this. And the question says you have to find a number of nodes that are involved into a complete binary tree.
Oh, then number of nodes who are involved in complete binary tree. Okay.
Yeah, I'm not saying number of all nodes, but only which are in the complete binary, which are involved in the complete. So like in this case, this one will form a complete binary tree. But if you consider tree rooted at here, it's not a complete binary tree.
Okay.
Does it make sense? This is a complete binary tree. So 3 will be counted, but when we consider this tree, it's not a complete binary tree. So anything above that will not be a complete binary tree. Now if you see here, this one is another binary tree. So we'll have total 3 plus 3 equal to 6 in here. But when you consider this one, it will not add up to the nodes. Is this clear now? Or?
Yes. So how you are thinking about the solution of this?
Yeah. So coming back to the original thing that we discussed, like when you go to any node, you just check this subtree whether this is a complete binary tree or not, and then you can, you can have a global counter called G, and you just keep adding the number of nodes. Suppose here you have one complete binary tree here, 3, another complete binary tree here, 3, another complete binary tree here, which is 3 plus 3 plus 6, 7. And you will have G getting incremented by 3 plus 3 plus 7. And once you reach to a node, which is not a complete binary tree, right? Because the subtree is just one child and you have 7 child here. Anything above that will not be a complete binary tree. Right? So any one of your child, if it's not a complete binary tree, the root cannot be a binary tree, complete tree. So it will be a recursive call, but every time you are inside a recursive call and you return back, you just have to return whether the node itself is a complete tree or not, and the number of counts, number of nodes inside it. So let me clear it out.
Wait a minute. Okay, yeah. Another approach you can do, if you do like a left-right route, what do we call post-order traversal, and continue passing this information upwards, like at what height your left or right subtree was when it started sending the information up. So for example, the last guys in any
I'm sorry,
uh,
your voice is breaking actually.
sorry, I'm in a bus.
Hello?
Let me try to be a bit louder. Can you hear me?
Yeah, it's just breaking a bit in between.
So yeah, start a post order traversal, I would say, and keep
Mhm.
passing the height, or depth, whatever you call it. So if the left subtree is passing a height 0 or depth, and the right subtree, the lowermost nodes I'm talking about, if they both pass the same information, the root looks at it. Hey, I can form a complete tree, and I can keep passing this up one by one.
Okay, so one of the scenarios that comes into my mind is this. I just okay, just take scenario. So let's say this is there.
Please name the node so I can be more clear.
In
Like
this case, this one will be a complete tree with a depth of 1, 2. This one will also be a complete tree with the depth of 2, but this one will not be. We have to ensure for completeness that number of nodes in this are the 2 is to power level minus 1. Then only we can say the left tree is complete for a tree rooted here to be complete.
Right. So can we also send this information while going up?
Right, so we'll have to see in two information, which is depth
Right.
and the number of nodes.
Right. We can create a data object which will have these two attributes, which we can continue pushing up. I'm
Exactly.
just thinking with you. Yeah.
Right.
By the way, for this particular question, that the last approach Sonia suggested, that is the expected approach. Because we are not using any property of the complete binary tree. All those other approaches were O of n, and that was the easy question. If you saw doing the regular queue approach or
Right.
DFS. So
For the ask question, that's the correct approach. We
yeah, and make sure that we understand that one. Yeah, because it's very important.
Correct.